So we begin some of the weirdest stuff in the world, although this isn't that weird. Today we will begin talking about the Heisenberg Uncertainty Principle, which stated, thusly, you can write that down. It says the smaller the uncertainty in an object's position, the larger the uncertainty in its momentum. And there are other statements of this, but we won't get into all that. We'll try to keep it as simple as possible. And I'll wait just a second to give people a little bit of time to copy that down if they like. That's a bunch of obviously meaningless words for a lot of people. So what we're going to do is we're going to spend the rest of this time trying to figure out what that means and why it means it. So the smaller the uncertainty in object position, the larger the uncertainty in momentum. So what do we mean whenever we say uncertainty? Well, first of all, mathematically there's a symbol for uncertainty. It's this little triangle, delta sign. And it basically shows how well you know something. A smaller uncertainty means that you have a smaller uncertainty means, of course, that you have a greater certainty, which means you know more. So the more you know about something, the smaller this delta thing becomes. Usually, if we're and the uncertainty can be for anything. It's about whatever you're asking. The uncertainty in someone's age, the uncertainty in a position, the uncertainty in a speed. It's a measure of something that you can measure how well you were able to measure it. So the example that I can give here is of a child. I have a child. I want to know where my child is, and I could say several different statements. I could say, I know that my child is within 100 feet of here. That would be a relatively small delta x. I could make it even smaller if I wanted. I could say that my child is within 5 feet of here, because I'm not saying where they are. I just know that there is a circle with a radius of 5 feet or 100 feet that I know they're somewhere inside there, or maybe I know they're in the next room, so I could say that. So that would be a fairly small uncertainty in position. So I have x here because x usually denotes like where something is. A larger uncertainty in position would be that, well, my child is in this town. I know that they're within 2 miles of here. So notice how the numbers, the x's are getting larger. We went from 100 feet to 2 miles. So I become less certain about where exactly it is. Or I could say, a different example, I could say, well, I have a very large delta x. I know that my child is within 15,000 miles of here. In other words, all I know is that they are on this planet. That would be a very large delta x. But that's what we mean when we say, when you see a term like delta x in the context of the Heisenberg Uncertainty Principle. I know in algebra delta means something different, but this is just a symbol to show this idea of how well you know something. And in general, the smaller that is, delta x is small, you know a lot. You know very precisely where something is. And the smaller that is, the more precisely you know it. Now, what the Heisenberg Uncertainty Principle says is that as that gets smaller, as you know more and more and more and more and more about where something is, then you must know the other number, delta p. Now p is stands for momentum. It's the symbol for momentum. Don't ask why. But you don't even need to know much about that. Just know that we're talking about movement here. So whenever we talk about delta p, we're talking about how well you know something's like speed or how it's moving. And so we have how well you know where it is and how well you know what it's doing. And what the uncertainty principle says is that when you know more about one, you must know fewer things. You must know less certainty about the other one. And so that is, if we go back up to the statement of the original, it says the smaller the uncertainty in an object's position, smaller uncertainty in its position, then the larger uncertainty in momentum. So where it is and what it's doing. So that is that's what we're saying whenever we rattle these words off. and that's a little bit of what it means. So then we can begin to ask reasonable questions like why? Well, why is this true? What does it even mean? Before we get too much deeper into this, you should probably know that there is a physical limit on how much you can know about something that you measure. That's one of the key arguments of the uncertainty principle. There's a limit. You can only know so much. And because when you know a whole lot about one thing, you change another thing. And so let's talk about, well, why? The thing you have to understand is that when you measure something, when you look at it, you are actually having to bounce things off of the thing that you're measuring, such as, let's take this example of a person. Here's a person, and this is my eye. I have an eye over here. I'm looking out in that direction to my right, and I want to see that person. Well, of course I can't. Not if it's dark. If it's dark, I can't see them. So what happens? Well, I turn on a light. Whenever I turn on a light, that light comes in, and the light hits that person, and the light bounces off of that person into my eye. And if that doesn't happen, I can't see them. So fundamentally, when I look at something, when I in effect measure it, I have to bounce something, light in this case, off of it. Usually light is a pretty convenient way to look at things, I think. And so we have to understand that first. So that is how we look at things. That's how we measure them. And in the lab, whenever we go to make measurements of tiny little particles, electrons, photons, this is essentially what we do, is we bounce other kinds of things off of them. So why then does this situation exist? Well, if we look at it, smaller wavelengths bring back more information than larger ones. And so I have an example here of a blue wave with a small wavelength and a red one with a larger one. And the small one will bring back more information. Let's imagine that you were trying to find out where this guy right here is. Like, where are you? Well, so you bounce some light off of him. Well, the uncertainty in what you see, or where he is going to be related to the wavelength, or about that. So let's say an uncertainty of whatever that distance is right here. Delta x is, you know, 1.5 inches, or whatever it is that you want to say that is. Whereas if I use a red wavelength, the uncertainty is related to its wavelength, which is like 8 inches. So it's a much larger uncertainty. So I know where this guy is. If I use this kind of light, I know where he is to within that degree of certainty. Whereas if I use this light, I'll know it to within that degree of certainty. And so you can get more precision or lower uncertainty out of high frequency light than you can out of lower frequency light. But if we recall, low wavelength, high frequency means big energy. And that matters, because if you hit something like an electron with a big amount of energy, you move it, you change it. So if it was moving this direction and then you hit it with a really high energy photon, you know, you're going to slow it down or speed it up depending on which direction you hit it in, and you're going to change what it's doing. So measuring that thing with light will change what it's doing, and the more you change it, the higher energy light you use, the more you change it, but also the more information you get back out. So there's a continuum here of how much you can change it, how much you will change it, versus how much information you want to get out of it, how precisely you want to measure it. So when you hit it with energy, it moves, and when it moves, the uncertainty and momentum goes up. In other words, you know less about what it's doing because you just changed it. I might know what it was doing a minute ago, but the measurement changed it. And so but when you do that, the uncertainty in x, or where it is, goes down. So I know more about what it's doing, but I know less, more about where it is, but less about what it's doing. So a different way to say all this, if we were going to restate that, we could say the more you know about where it is, the less you know about what it's doing. That is a general way to rephrase the Heisenberg Uncertainty Principle in a way that makes a little bit more sense, doesn't have all the weird symbols, but you can kind of summarize it with that statement. And this introduces the quantum measurement problem. This is kind of the first time that we'll introduce this. We're going to see in the next few days a lot of really weird stuff that happens as a result of this quantum measurement problem or other manifestations, but this is actually the least mind-blowing one. It's pretty straightforward. You physically interact with a system to find out information about it, and you change the system. And Heisenberg quantified that. There's a formula that says exactly how much you can change and how much you can know. But we won't get into any of that stuff. I just want you to qualitatively understand how that works.